Welcome students to my channel PRADIP sir classes as BSc, and today's I discuss with the that particular part that is a uniform electric field is given, and if we placed an electric dipole within that particular uniform field, then what happens? So uh, electric dipole placed within a uniform electric field. So first of all, students, you have to know what is uniform electric field, and we can represent a uniform electric field like a equidistance line. So this is uniform electric field, and this is from left to right, and if we consider it is inward, then we can represent like that. That is equidistance cross. So equidistance cross means it is also a uniform electric field, but directed away from the viewers. And if we are reader, then that particular direction it indicates that particular field. And if it is outward towards the viewers, towards the reader, and if we read a particular book, then along this direction, and that is represented by this one. And if we consider a arrow, then this particular tip when moves, that is the tip, and when it towards the particular papers, then we can see the cross of this one. So it is when the electric field is into the surface, then this is that particular ones, and when it is away from or towards the reader, then this is a uniform. What is uniform electric field? It is the representation symbol, but what is the uniform? And so the definition is, if we placed a unit positive test charge, within a field, then it experienced equal electrical influence. So if we placed a particular charge, unit positive charge, suppose Q0, within that particular field, then it experiences an electrical influence, that is electrical force, and that is equal at every point. So this is called uniform electric field, and the representation mark is, you can represent it like that one, that or that. When it is from left to right, then this one, and if the electric field is suggested that it is from right to left, then you can write down like that. And when it is into the surface but perpendicular to the page of the books, that is away from the reader, then it is taken as equidistance cross, and if towards the reader, then it is taken as uniform dots. So electric dipole placed within a uniform electric field. what is an electric dipole? Students, we say that the previous class, and if you are the first in that particular channel, then please pause the video and go to the previous lecture. So this is minus q and this is plus q, and if two equal and opposite charges separated by a very small distance, what is the significance of this small distance? And it is very much negligible, and you go to a particular molecular level. So this is suppose this is a minus delta and this is plus delta, so it is a dipole, it is an electric dipole. So when two equal and opposite charges separated by a very small distance, then this is called dipole. And if we take that particular distance as this is, if say 0, then it is L, and it is also L. So the total distance of separation we can take as 2L. For easy calculation method, you can take this as D, then this one is D by 2 and this one is also D by 2. So what is an electric dipole? If two equal and opposite charges separated by a very small distance, negligible distance, that is of the order of minus 10 to the power 10 meter. So this is angstrom level, 1 angstrom equal to this meter. So then we can say that this is an electrical dipole. So the next question is, an electrical dipole is placed within a uniform electric field. Is that clear? I think it is so simple. Electric dipole, when placed and we can place this one with that particular field, that is minus q and plus q, like that. You can place here as minus q plus q, that is along the line, and you can anti-parallelly we can place it plus q minus q, or to any one of the angle. Then what happens? When we placed that particular charge within a non-uniform electric field, this is minus q, this is plus q. So all the questions arise within your mind, and I think I discussed today. So wait and clear all the concepts related with an electric dipole when placed within a uniform or non-uniform electric field, and what happens. So first of all, we can take into account that particular uniform electric field and we place that dipole within that particular field. So let's start and take a uniform electric field first of all and placed that particular dipole. Okay. So, and this is the electric field that is uniform and that is shown by the equidistance line, and this is minus q and this is plus q. So students, we know that dipole moment. What is dipole moment? Now it is the product of any one of the equal charges and the separation between them, that is taken as 2L. So P equal to Q into 2L, and it is a vector quantity. Dipole moment is a vector quantity. What is dipole moment? Then you have to write down that a dipole moment is the product of any one of the equal charges, any one, that is you have to take the magnitude only, and the separation between the two charges. So this is dipole moment, and dipole moment is a vector quantity and it is directed from negative to positive, because when a particular physical quantity is vector quantity, then it means that this is possesses magnitude as well as direction. So students, this is electric field, and electric field is not the function of R. means the intensity is same at everywhere. So this is an electric dipole, and that particular positive charge can experience a force, because we know that electric field equal to force by charge. So force equal to QE. So force equal to QE, since it is a vector quantity, then F vector equal to QE vector. So that particular charge can experience an electrical influence along the electric field, that is from left to right, and that particular charge, that is minus Q, can experience an electrical force along this one. So this is QE and this is QE. This is QE. So students, for positive one, the force is, electrostatic force is QE, and if we take it is a vector quantity, then it is along, suppose this direction is along n cap, suppose this direction is along n cap, then that particular direction is taken as minus n cap. So this is n cap. So F vector equal to QE into n cap, and due to this one, take a particular name A, this is A and this is B, so FB equal to this one, and FA, and what is FA equal to QE into minus of n cap, so the net force, so F net equal to FA, and this is a vector, FA vector plus FB vector. Net force equal to sum of all the forces acting on that particular type. So this is QE minus n cap and plus of QE and n cap. So that is 0. So we can say that the net force on that particular dipole is 0. Net force on that particular dipole is 0. But if we placed this one along this direction and can apply a force along this direction and along this direction, then it rotates. So when the net force is in that particular case, the net force is 0, but still acts a torque, that equal and opposite forces can create a torque, and that particular dipole moves or turns along a particular direction, because we know that when torque is applied, then it that is, torque is the turning effect actually, so it can rotate in clockwise direction, because QE acts along this direction and this direction, so to apply it. What is then the question arises that what is the value of this torque? So for calculating that particular value, we have to take into account the particular triangle, and this is the angle. So that particular dipole is placed with an angle theta with the electric field. So this is point C. So the torque, what is the amount of torque? Torque equal to torque, you can represent it as tau. Tau equal to equal forces, any one of the equal forces. So any one of the equal forces, any one of the equal force into perpendicular distance. What is perpendicular distance? Suppose this is a steering. Suppose this is a steering, and you can act with your right hand along this direction, and another forces act along that particular direction. So the diameter of the steering is here the perpendicular distance between the equal forces. So here this is not the perpendicular distance, because the line of action of this force is along that direction and along this direction. So the perpendicular distance is this. This is the perpendicular distance. That is, here it is BC. Here it is BC. So the next is any one of the equal force into perpendicular distance, perpendicular distance between the equal forces, So any one of the equal force means here it is QE into perpendicular distance. Perpendicular distance means BC. So what is the value of BC? So this is BC equal to, you can take here as sine theta. So sine theta equal to sine theta, and this is equal to perpendicular by hypotenuse, and here the distance is 2L, because we can take for easiest calculation, that is the distance between the two opposite charges is 2L, that is the length of the dipole. So sine theta equal to perpendicular, that is BC. This is the acute angle. So if we take that particular acute angle, then this is the perpendicular, this is base, and this is hypotenuse. And if we take that particular angle, then this is perpendicular and this is base. And if we take that perpendicular, if we take an axis like that and take this angle, then this will be 90 degree minus theta. So that's will be, if we take that particular direction, then the derivations is transformed into another form. So sine theta equal to BC by hypotenuse, that is 2L, or BC equal to 2L sine theta. 2L sine theta. So BC equal to, therefore QE into 2L sine theta. 2L sine theta, that is torque. So torque equal to, students, QE into 2L sine theta. QE into 2L sine theta. Yes, so Q into 12 means P. So Q into 12 means P. So PE sine theta, tau equal to, since tau is a vector quantity or not? Tau is a vector quantity. Torque is a vector quantity. So how can we represent that particular three quantities, that is tau, P and E? So what is the direction of P? Is a vector quantity. P is a vector quantity, and electric field is also a vector quantity, and tau is also a vector quantity. So all the three are vector quantities. So you have to take a cross product. So tau equal to, we can write tau vector equal to P cross E. P cross E, because P is sine theta. This is only the magnitude. This is only the magnitude, P sine theta. So tau equal to P cross E. Since tau is a vector quantity, then tau equal to P cross E. And the next step is, what is the direction of that particular physical quantity, that is electric dipole, the electric field, and the torque. So the next one, if we draw that particular vectors, physical quantities, and then, and suppose this is negative charge and this is positive charge, so the direction of that particular vector P equal to along this direction, from negative to positive, and the electric field acts along this direction, So you can apply the screw rule, right-handed screw rule, or so simple rule, that is bottle cap rule. And if we turns along this particular direction, the PQ, then it is towards the thumb, it direct towards the thumb, that is inward direction. So you can say that here it is crossed, because along this direction, means towards the into the paper. So if we show you with that particular pen that this is the P vector and this is E vector, so this will be the torque, cross. And if we show that this is P vector and this is E vector, then P cross E means this will be the direction. This is P, this is E, then this will be the direction of tau. So P crossing means you have to move from P to E, and that will be the direction of torque. And if we suppose if you tighten your bottle cap, then the bottle cap moves towards that particular board, and if we open that particular one or bottle cap, then it moves towards U, that is outward. So here it is, this is the direction of torque vector. So this will be these all the vectors. So the direction of tau is along this direction, and if we take that P cross E, then it will be towards the reader, and it is away from the reader. And so this is the value of torque. And next step is where that particular torque is maximum, minimum, or it may be 0. So the next one is where that particular field, yes, and this is no, this is torque. So where that particular torque, so torque equal to PE sin theta, PE sin theta. So this is the simplification. And if we placed an electric dipole within an electric field, then it rotates. And the moment of this couple is tau equal to P sin theta. So if we placed that particular dipole along the direction of electric field, suppose case number one, that is this is the electric field, and the dipole is placed like that. This is minus Q and this is plus Q, like that. Then we know that the positive charge always moves along the direction of electric field. So the electric field can create a force of QE along this direction, and for that negative charge, this force acts along this direction. So suppose, students, if we draws this pen like that, if we draws along this directions and with our left hand along this direction, then it can't rotate, because there's that particular two equal forces can balance that particular dipole. So here the torque is PE sin 0 degree, because what is the direction of this B vector? That is from negative to positive. And what is the direction of B vector? Along the same direction. So P cross E means P sin theta, sin 0 degree, that is sin 0, 0. So the torque is 0. So this is 0 torque. Next, case number 2. Case 2. And if we place that, this is the electric field, and the dipole is placed, along anti-parallel with the electric field. So this is minus anti-parallel. What is anti-parallel? Because the direction of the dipole moment is taken as negative to positive. So along this direction, dipole moment act, and this is the direction of electric field. So this is anti-parallel. So tau equal to PE sin 180 degree. PE sin 180 degree, that is minus, since the sin 180 is 0, so this is also 0. So this is a case of, suppose if that particular two forces acts along like that, and I can show that particular forces. Suppose this is the first case, and if we with our right hand we can apply the particular force QE along this directions, and with our left hand along this direction. If we force that particular two forces are acts like that, then this is the torque is 0, and the torque is 0. But if we displace this pen, then it rotates. So this is the unstable position, but this is the stable. If we displace this one, then it can't rotate. And if it rotates, then it within a second it can attain at equilibrium position. So this is the stable equilibrium, but this one is the unstable equilibrium. So the next one is case 3. Case 3, when we can place it like that. This is the electric field, and if we place that particular dipole along this direction, so this is minus q and this is plus q. So this, the direction is 90 degree. So the torque tau equal to PE sin 90. So sin 90 means 1. So PE. So torque equal to PE. That is, this is the maximum value of the torque that acts on the dipole. So students, let's explain that particular one with an example. Take an example to realize that particular cases. Three cases. So we can erase that portion. Suppose students there is a cauldron, okay, or anything curved surface, and if we placed a marble here, then what happens? If you displace this marble, then it attains an equilibrium position immediate. But if so, we can say that this is a stable equilibrium. But if we placed the marble like that, then the marbles, if we displace a small portion, then it falls. So this is the 0 degree position and this is the 180 degree position. These two are equilibrium. But if we displaces a little that one, then it attains immediately. But if we displaces this one, then it falls. So this is the unstable equilibrium. So this is the unstable equilibrium. And the next one is to think that if we place the marble at that position, then it goes here within a second, because this is the position, this is the particular position where the force is maximum. The force means that is the force is QE, but the couple is maximum. So this is the maximum torque position. So when we place dipole moment or electrical dipole within an electric field, then it rotates. If we place like that, then it in a stable equilibrium. If we placed here like that, then it is an unstable equilibrium. That is, if we displaces it, then it rotates and turns into that particular position. And if we placed that one, then the maximum torque acts. So these all are the concepts about students when an electric field is placed within a uniform electric field. But the question is that if that particular field is not uniform, that particular field is not uniform. Students, take an example. The next question is, if the dipole is placed within the non-uniform electric field, then what happens? So first of all, students, clear your concepts about uniform and non-uniform field again. So suppose there is a charge Q and it can create a field. That is, suppose since this is positive, then it creates a field along this direction. And we students take some area, equal area. And take an equal area at here, then at that particular position, then at that particular position, and that particular position. So this is position 1 and this is 2 and this is 3 and this is 4. So if we compare 1 with 2, then where the electric field intensity is maximum, then you easily say that this is, since this is E1 and this is E2, then E1 is greater than E2. And why? If we say why, because you say that the electric field lines crossing that particular area is maximum with respect to this one. So where the electric field intensity, electric field lines are gathered, then at that particular position intensity is also maximum. So here intensity is maximum with respect to this one. But if the question is E3 is also greater of this one, then it may be right, but we can say that the number of electric lines of force along that two different areas are nearly equal. So we can say that E3 is nearly equal to this one. So what is a uniform electric field? So we can say that at that particular region the electric field is maximum and represented as equidistance line. So this is uniform electric field. So uniform electric field is an approximation, and no charges can create electric field, a uniform electric field. So these particular charges can create a non-uniform field, and if we place the dipole within that particular non-uniform field, then what happens? And if we placed the dipole along that particular field that is within the uniform field, then the net force is 0. Then the net force Fe equals to the net force F net equal to 0, but torque is Pe sine theta. But if we placed within the non-uniform field, where the field is non-uniform, this is a particular line, this is a particular region that is uniform, this is the approximation. So let's take an example. So the example is, suppose the students think that this is a boy, and when he runs the comb with his or her dry hair, then it acquires, it loses electron or gains electron. Suppose it loses electron, some electron, so it is positively charged. So the comb is positively charged when it runs over his dry hair. So at that position, if we placed this one here, and there it can create an electric field of intensity at different places. This is not uniform electric field. So this is, it can create, the comb can create a non-uniform electric field. And suppose there is a bits of paper here. There is a bits of paper here. Then this comb is positive. This comb is positively charged. So the field is away from that one. That is outward direction, and it can induces a negative charge here, and the positive ones is this. So at that particular position, we can say that negative and positive charges are separated by small difference. So it is electric dipole. So electric dipole. So this is dielectric. This is not a conductor. So dielectric, when dielectric placed within a non-uniform electric field, then the positive and negative charges are separated and an electric dipole is produced. So this is an electric dipole and placed within the non-uniform electric field. And what happens at that moment? That is, these bits of paper, you know that if we rubbed a comb or runs over our dry hair, and a bits of paper are attracted with that particular ones. So this is moves along this direction. Is it rotate or not? No, it is not rotated. It just moves towards opposite to the field. So the question and the answer is that if we placed, this is the field, this is an electric field, and it is a function of R. So the electric field at that particular region is greater. This is E1, and this is at that particular one, so it is E2. And if we placed a dipole that is minus Q, and this is plus Q. So the plus Q can experienced by force plus Q. This is the direction of electric field. So the plus Q moves along the direction and the minus Q along this direction. So this force is QE1 and this force is minus of QE2. And where the force is maximum, and then usually say that this region the electric field intensity is greater because of the congested of the electric field lines. So QE1 is greater and QE2 is less. So QE1 is greater of QE2. So the electric dipole moves along the electric field. And if this is not so, if the field lines is like that, it is a function, electric field is a function, and electric field directed like this, and if we place the Q and minus Q, so minus Q can attracted along this direction with a greater influence and this one with a less influence, and that particular dipole moves opposite to the electric field. So this is the concepts, and I think you that is will be clear to you. That is, if we place the electric dipole moment, electric dipole within a uniform field, then it can rotate. That is, the net force is 0. So the first one is the net force is 0, but it can rotate. But the second was in when we place the within the field a non-uniform electric field, then it moves away towards the field. If we placed it is in along the field or anti-parallel. Along the field or anti-parallel. So all the concepts I think clear, and wait for the next class, and next class must be about potential, or it may be numerical. So let's memorize all the electrostatic. What is electrostatic? So electrostatic is a charge. Electrostatic means charge. Electrostatic means Coulomb's law, when the point charges are kept at a small separation. Electrostatic means superposition principle. This is Coulomb's law. This is when the charge is more and more gathered at a particular position, and if we calculate a particular force upon a particular charge, then we can apply superposition principle. So superposition principle. So Coulomb's law means charge, that is losses of charge, there is gain of charge, there is deficit of charge, there is the excess of charge, that is charge, all about charge. And charge can experience as a force, and we can calculate these interactions with the Coulomb's law, and if it fails, then we can calculate superposition principle, and if this one is also not applicable for that one, then we can apply charge distribution process. Charge distribution process, that is integration process. We can calculate that particular forces one, and if this is also filled, then we can apply Gauss's theorem. So Coulomb's law is charge. Coulomb's law. So electrostatic means charge. Electrostatic means Coulomb's law. Electrostatics means superposition principle. This is one charge distribution. This is Gauss's law. And when a charge is kept here, it can create a field. And if we placed another charge over here, then some work is done on this particular charge. So when we kept a charge along near another charge, then external agent must work done on that particular charge, and this work done is stored as energy. So the next one is potential and potential energy, and when it stores, then it is called capacitor. So this is all about electrostatic is a branch of physics that deals with the charge at rest. So thank you, and wait for the next class and continue your study.